Okay, now we are all there. So, good evening, everyone. This is Celso Batalla, Introduction to Astronomy Online. And few things I would like to let you know. We have an exam tomorrow, and I sent an announcement indicating that chapter 5 and 6, telescopes and light, would be in the exam, but they will not be in the exam. And I stripped all the questions related to these two chapters out, which I might have left some in, probably not. So if I do, I just cancel that. I cross it out manually. Otherwise, it's going to be everything up to yesterday, what we covered yesterday, which was the interaction and relation between Moon and Earth. There will be lots of questions regarding the Moon, Moon's phases and eclipses and seasons. So all of that you have to be okay. And as I was commenting before, if you want to be proctored by me, meet me in SA111, which is in the New Science Building at 4 o'clock. And then you have 1 hour to complete the exam. Or if you prefer to do at home, take your computer, make sure you have Google Chrome as a browser, and go to Canvas course, and then install the extension Proctorio. So that extension will find the camera in your computer or a camera that happen to be attached to your computer and have access, have control over it. And so as you do the exam, it's gonna check your eye movement. If you kind of look around or do something, it will flag, and then I have to check and see what's going on. Yeah, it looks like a big brother in the other, you know, the other side of the table, but that's what it is. Or you meet me at 4 p.m. in room SA11, the new science building. The exam tomorrow, you have one shot, and usually I give a second shot, not necessarily the same questions, a couple of days later. So tomorrow is Thursday, so on Saturday you have a chance of doing again, and I will collect the high score of both attempts. If nothing happened, it's a good practice, so we can crystallize more the type of information we are sharing here. So any question before I start? All good?
Actually, so if we decide to do it online with the Proctorio, is it going to be the same time as well, just 1 hour?
It's the same time. It's the same
Okay.
time, yeah. And
And
the way you do, if I recall well, so the Proctorio opened the exam, and then you see the exam there. It's coming one question every time, and let's see how that goes. So one question each time. You show your identification to the camera,
yeah,
so I know who you are, and you show your cheat sheet back and forth. Then you put it there on the side. You might have your book there. I don't know. You shouldn't. And then that's how you do the exam. You cannot leave the room. You cannot have somebody there because the camera will flag that. The software will send me some red flag on that.
okay. And would we be able to go back to a question, or is it just going to be one after
Yeah,
another?
no, you can go back. You can go back, but always one question at a time. You don't see
Okay.
the whole thing. You cannot shrink the window. You cannot have a second browser. You can, yeah, all these things. So you basically will see Proctorio and the symbol of it, the icon, and the question, multiple choice question below. Then you answer.
Yeah.
Okay.
Okay.
Any other question? All good. Okay. So when you think about science, science is a method, or I think I mentioned this before. It's like a window that allows you to see how nature behaves and gives you the tools to describe this behavior. Science does not deal, although people think Science does not deal with absolute truth. Like, this is truth because the scientist said. Not at all. In fact, science works attempted to negate previous, previous statements. So all the theories we have, or you might have been introduced to some before. Like yesterday, I introduced you to the law of gravitation. It's a theory. The theory is based on the fact that mass attracts mass with an intensity that depends on the product of these two masses divided by the distance between them square times a constant. It's a theory. So this theory is able to predict movement of bodies, celestial objects, with very good precision, and it fails under certain conditions. But for all purposes, it works nicely, very nicely. So, but it works quite well up to the end of the 19th century, when um, relativity came. And then general relativity now is the one that can explain better with more details. And, and the theory that I introduced yesterday is a particular case of this general theory of relativity, right, that describes the motion of celestial objects out there. So just to say that theories are not the ultimate truth on how nature behaves, but if there is a theory out there, the theory should be able to explain all the behaviors we are able to collect data for and also make good predictions. If the theory make predictions and you collect money and develop the theory to measure one of these predictions and doesn't match, so what you observe does not conform to what the theory was saying, then you have to either modify the theory and improve it, or you have to discard. Um, and in it, in this statement, is the argument that science is always evolving, is evolutionary, as opposed to, for instance, religion. In the framework of religion, you have certain so-called absolute truth. For instance, God created the universe. Let's say a religion have that statement. You cannot disprove that. You cannot negate that. You cannot summon God to a laboratory to measure its property. You cannot do these things in the realm of science. In the realm of a religion or a belief system, you can. But if you negate this statement, this so-called truth is inside a religion, you are not within that religion anymore. You are in a different sort of religion. It's a different language. It's a different set of parameters or premises. In science, is different. You have a language that is universal in the sense that the science that is done in the United States is the same in Russia, the same in Brazil, and the same everywhere. And it's based on we observe, we establish hypotheses. These hypotheses are needs to be verified. All the arguments used in the hypothesis must be verified. I cannot say that stars rise in the eastern sky because you have angels lifting them up from the eastern part because it's sacred. You cannot say that because angels, you cannot bring them to the laboratory, basically. Uh, and and um, and once uh, you want to know about some object, you bring it to the laboratory and you dissect and you use uh, tools that are nothing but the extension of your senses. So tools that allows you to see better, like microscope, or tools that allows you um, to touch better, in mathematical language. So all of that is part of what we call the scientific method, as we discussed in chapter 1. Why am I doing all this monologue? Because the objects studied in this course, astronomy, you cannot bring to the laboratory. You cannot bring, for instance, a galaxy to your backyard so you can, measure properties. You don't do that. You We might have some samples of solar system objects like planets, maybe Mars. We might have samples of Moon, and we do. We might have pieces of asteroids falling down, and might collect some of it. We might use that to study the history and the origins of our solar system. But objects such as galaxies or Andromeda galaxy, quasars, interacting clusters of galaxies, we cannot bring them. They are too big and too far. So, how can you establish knowledge? How can you establish information about all these objects if, first of all, we cannot bring them and put in a laboratory? Second, we cannot go there and visit them because we don't have the technology for it. So, the answer lies in the light. So, light is something, and that's the point of chapter 5. Light is something that interacts with matter. And when light interacts with matter, it takes properties of material objects like temperature, pressure, density, the density of gas, what type of motion the gas is having, is going towards us, away from us. So light collects all that information and sends that information through space. Eventually arrives here on Earth. And then astronomers with a telescope collect that information, funnel that to detectors. Like your cell phone have detectors. So use that to take pictures. Astronomers do the same, but with the light. So collect this light, put in detectors, and send that to computer and analyze. By analyzing this light, we can infer the properties of these celestial objects without going there. So the importance of chapter 5, although it might appear to be dry and full of physics and so on and so on and so on, is very important because it explains how, first of all, what light is, and how light interact with matter, and how properties of matter happen to be impressed in light itself. Okay. Uh, in section 5.2, it shows light as a display of electromagnetic radiation. And let me show you up here. You all can see this, right? Okay. Excuse me. You have a gamma rays, X-rays, ultraviolet, and visible, infrared, microwave, radio, and longer radio waves. So light is, and when we study physics, we learn that light can be interpreted, in fact, can be measured in two possible ways. If you have certain types of detectors and experimentation and experiments, you can prove that light behave like a transverse waves. Like if you go to Santa Cruz Beach, you see these nice waves coming in. So those waves are called transverse waves. So if you are a surfer and you are in the water on top of a board, when this energy comes, this energy take you up and down. So you move in a direction up and down that is almost perpendicular to the direction in which the wave itself moves. So those type of waves are called transverse waves. So light, for all purposes, and if you take our Physics 4C course or Physics 2B, you're going to see some of these properties being demonstrated in the laboratory. We can prove that light is a wave, is a transverse wave. We don't have the experiments, but we could measure the speed of light with very good precision, 300,000 kilometers per second. And we also could prove to you that once you take the light and you force the light to go through a prism or you can take the light and breaking down the light in its different frequencies. We show that the visible light, the one we see, I mean, you look around yourself and you see all kind of a players of colors around. Those colors we see is just a small fraction of the entire range of energy that what we call electromagnetic radiation is able to provide. So see this kind of a little slice over here with the yellow, orange, and kind of a purple. This is what we see. This is the visible light. But at a shorter wavelength or higher frequency, that comes the ultraviolet radiation. X-rays that you might see in your dentist. Your dentist might have some machine that use X-rays because it's very energetic. It's high power of penetration and uh, can take a inside view of your body, your teeth, and even more energetic gamma rays gamma rays. Shorter wavelength, very energetic. So the light associated with the gamma rays is a light that is produced in exploding, fantastically exploding events like supernova. You have gamma rays being produced. You can have gamma rays being produced in the very core of stars, in the furnaces where um, atoms are being formed because of the high density and the high temperature this core hosts. And in few days, next week, in fact, we are going to study evolution of stars, and this subject will come back. So X-rays, Superman and Supergirls have have X-rays vision, which is kind of a bogus. So X-rays vision, if Superman exists, first of all, and uses X-ray vision to see inside people or what's going on, everybody would have cancer, right? Everybody would have to use some sort of protection. So X-rays is energetic, but we have a nice protection in our atmosphere also for ultraviolet. The sun does not produce lots of ultraviolet radiation, but it produces some, but our atmosphere blocks most of it. And because of that, life could in fact develop here on Earth. This ultraviolet radiation is not as energetic as X-rays, it's less energetic, but has the power of breaking down macro big molecules. So when life was developing here on Earth, it could only migrate to be inland once we had set a protected sheet around Earth of gas named ozone that blocks most of this ultraviolet radiation. And then you have the visible range we see. I mean, the sun, our star, is peaking most of its radiation or most of its energy come or is produced in this visible range. It does have some UV, but not as much as the visible. It does have some X-rays, nearly not as much as the visible, so it has some. So because the sun is producing most of its energy in this small slice, we and life here on Earth adapted to that. And then we developed these sensors here, our eyes, that are capable of interacting with this prominent and abundant radiation and transfer information to the brain, and then we make sense of our own environment. So the sun also produces infrared, but not as lot. And microwave is a you have a device in your kitchen that uses microwave type of radiation because microwave is easily absorbed by water and vapor. And so when you put food in the microwave, you send this energy, this transverse wave, that is a very long wavelength compared with the visible. Uh, and this radiation is easily interacting with water. So it warms up the water in the food, and then you have the food being warmed, basically. And then you have radio that is primarily used in communication, as you well know. Now, what is being shown here is the window through which we can see things coming out of the outer space. For instance, in the longer radio waves, you don't see transmission in our atmosphere. Our atmosphere is said to be opaque to this longer wavelength. Look at infrared. There is a small window of infrared radiation is here represented by these two bars that if you place a telescope with a detector in the infrared exactly at this particular wavelength, you can see anything. But all this microwave, all this infrared, you don't see it. Therefore, if you want to do any science that involves microwave radiation, then you have to use space technology so that you are flying and you're putting your detector above our atmosphere that works as a filter to this type of radiation. The visible light is not a problem. Go all the way to our telescopes. Although the atmosphere interacts and interferes slightly with the image, and there are phenomena called seeing. We are going to see this later. And then using space technology is always a plus. You have a small window of UV, but everything else is blocked out. Our atmosphere blocks the ozone, blocks most of this type of radiation. Now, we see with our eyes the visible light, right? That's what we see. But if we had radio eyes, our universe would appear to be completely different. Stars do not produce radio radiation in abundance as they do um, the visible radiation. Radio emission occurs in extended sources, in gas that happen to be in the galaxy, spread in the galaxy, not concentrated in stars. So our perception of how the universe would look like would be completely different had us eyes that were more sensitive in the radio band, okay, or any other particular band that is not radio. So we have an intrinsic bias on how we understand the universe is because of our senses, basically. Now, what is being shown here is what's called black body radiation. Am I going to uh, describe this to you? Not at all. Um, if you take our physics course, we invest time explaining these processes here. But I have to tell you that stars behave like black body. And what is a black body? A black body is an object that is able to absorb energy or electromagnetic radiation in all possible frequencies. But once it absorbs this energy, it sends that out in all possible frequencies. So it's spread out in all possible colors, if you will. So let's say there is a black body and you shine a laser beam that is a green laser. You shine the green laser on it, so that object, black body, take this energy and then is spread out in all possible colors, so that if you could open a hole in that black body and look it inside, you wouldn't see that prominent laser beam in there. So black bodies are capable of producing their own energy. They have an internal source of energy that produces that. Whereas the light that you see coming out of, I'm seeing green light around me, I can see trees, I can see the blue sky. All this radiation that I see with colors, these colors are reflected colors from the sun. So the green that I see in the trees, the leaves of the trees are greens that are being rejected by the plants themselves, and every single other color band from the white sunlight is being absorbed and used to operate its chemistry. If somebody has a red jacket, the red is being rejected whereas the bluish, the violet, the green part of the wavelength um, spectrum that is being absorbed by the jacket is being used to give warmth and energy to that person. So a black coat, for instance, is ideal for winter because the black absorbs everything and does not reflect or emit anything. In fact, it's going to emit uh, in the infrared part of the spectra as heat. Um, why is this important? Because the stars are black body. In stars, they are not exactly, but they behave like a black body. So if you go to the observatory in July 20, the moon is going to be in the sky. It's not a good time to see, but there are certain stars that when you look at them, they appear like this 3000 Kelvin curve over here. They appear reddish. Then, for instance, the stars like Vega, there appears to be more kind of a whitish and hotter. So let me show you an animation that might exemplify what I'm trying to say as far as black body radiation. And for that, I'm going to go to my uh, NAP Astro modules. And I go to my class actions and I choose simulations. And there is a nice simulation here on. By the way, you guys could explore if you want to learn more stuff about astronomy. This is such a great resource. Light and spectra, black body curves. Oh, I don't have any media. My flash is old. Let me get another one. Just a second. Sorry about that. Class actions, simulations, and then I go down to black body. And what is it? It's right here. There you go. So this is so if you take the white light and you spread out, you see the different colors as we saw previously. And to the left of these 400 nanometers, this is a scale of wavelength. So to the left of it, you have the ultraviolet short wavelength, and you have X-rays, but it doesn't appear in here. And to the right, you have infrared and microwave, which also doesn't appear in there. So here, 300 Kelvin. Kelvin is a unit of temperature that is given by Celsius scale plus 273, the number 273.15. So 300 Kelvin is the equivalent of 27 degrees Celsius, more or less, which is a nice temperature. Is the environment, the ambient temperature we all have now, 70 Fahrenheit or so. So it's a good temperature. Now, here is a circuit. So you have an insulator, so somebody's holding this wood over here. There is a nail that is a conductor, and somewhere here, which is not shown, there is a power supply that is sending current through this circuit. Okay. And then what are you going to do once you start this animation? Current will be going in, and this nail will start warming up. So see what happened, and pay attention to this curve. This is all dark, right? There is no light, and the nail is warming up. Go from red, yellow. See the curve coming in, and it becomes almost whitish, but it can't handle anymore besides vaporizing, and it breaks down. Pooped. And then the circuit is closed, or at open, I mean, and then no more current flows, and that thing cools down, the black body goes down. So if I go back here, right, you have a light, turn it on. So turn on the light in your room, so you get that, right? Now, when I start the animation, it's as if you turn off the light in your room and the only thing you see is nothing. But then as the nail starts to warm up, you see some dark red color coming in. And then you can see the black body being developed here. And I'll show again. So there you go. And the hotter it becomes, this black body start peaking more in the blue part of the spectrum. So when you, in a very clear night, if you happen to look up to the sky and you see kind of an electric blue or white stars, those are the hottest possible. And the stars that are kind of a reddish, they are the coolest possible. Okay, that's the idea. And stars, they are not exactly black body, but they behave such as a black body because light is somewhat trapped in the star, first of all, and stars are capable of producing their own energy. If you shine energy into a star, it's going to take that and reprocess that energy and send out to all possible wavelengths. Oh, I lost my class. Where's my class? There. So if advance in the book, this equation is Wien's equation. I might have, you might be lucky enough to find it in a homework, but don't worry about exam. I don't put math in exam. But this symbol here, lambda, is a Greek letter that tells wavelength. It is showing that in that black body curve we just saw the peak of it. So where most of the emission comes in a wavelength, which means in a color that is inversely proportional to the temperature. In other words, the bluer the star is, the hotter it is. So which means the shorter the wavelength is, uh, the which means shorter means a smaller wavelength, a small number here, is because this t is too big in the denominator, if you remember your math. So which means hotter stars, high temperature, are those with smaller wavelength. Conversely, those with longer wavelengths, so those red stars, are those with smaller temperature. Okay, that's so-called Wien's law. Now, the last thing I would like to talk to you is one of the important tools in astronomy, and that is called spectroscopy. Spectroscopy. So, what spectroscopy really is? Spectroscopy is a science by which stars send out light, and you take this light and you break down. So, this is a starlight. You break down in its different components or colors. Now, astronomers use very powerful spectrometers. They are able to spread out this rainbow in such a way that when this is done, like this, and when this is done, you find that this rainbow is not just a rainbow from red, green to blue, but it shows a lot of these little dark lines. See that? All these dark lines. These dark lines are called transition lines. And what the heck is this? So transition lines occur because the fundamental building blocks of nature are called atoms, and these atoms are consist of positively charged called protons in the very nucleus and central part of these atoms, and they are surrounded by electrons. And electrons, as you go to the atomic level, there are laws in nature that forbid electrons to be anywhere. They are forced to stay in what we call orbitals, in very specific regions around the nucleus. Now, if you give energy to the atom, electrons can jump from certain orbitals to another, but it can't stay in between them. The best way I have to explain, the best simulation, if you want to explore later, is also found in this simulator for the hydrogen atom. So here's a model of a hydrogen atom that has a proton and an electron. And what I'm going to do, I'm going to fire a photon, a wiggly photon, and nothing's going to happen. But if I fire again, nothing's going to happen. So let's say if I take a more energetic photon, I'm sorry, yeah, a more energetic photon, more wiggly, nothing happened. But if I take this photon and I fire a precise frequency, see what happens. So the electron go to an upper orbit, and when it comes down, it fire up that photon, but in a different direction. Let me do it again. The atom absorbed, send the electron to a orbit, and then when the electron goes back to its original orbit, it fires up some radiation. In other words, when light, like this photon, enters a region in the stellar atmosphere that has atoms that like to absorb selectively at those particular frequencies, what the final product is all these dark lines. So the photon, which is energy, which is part of that rainbow, is depleted, is absorbed by the atom. And then what you see is a lack of that photon because that photon was spread in a different direction. Now, if you become an astronomer, if you like this subject so interesting, you know, that you, okay, I want to be an astronomer. I want to be a graduate student. I want to spend the next 4 years of my life doing all this fun and exciting studies. One of the things you do is to go in fine detail and look in very large precision these absorption lines, and then you find all kind of kinks, all kind of asymmetries, all kind of things, and the depth of the line, the broad, how broad the line is, and then you use all this information to infer the properties of the star. So that's what spectroscopists do. Um, if you like shows like CSI, uh, they do the same thing. Somebody kills somebody else, but had a perfume, and then the CSI team goes to the to the crime scene, and then you smell some perfume, and they go to the bathroom of the victim, and they don't find the perfume in there. So what they do, they take a sample of that atmosphere, that gas, take to the laboratory. They shine light on it. The wiggly light interact with the gas, and then they print a button, and that comes a printout with a bunch of molecules or spikes, and the spikes are identified certain molecules that are part of a certain perfume. So these molecules, this science basically spectroscopy, right, is when you have a gas and you allow light to interact with matter, and when that is done, you have these transitions being made. So in the structure of atoms, that's what you learn, that atoms are made of protons, neutrons, and electrons. The easiest model possible is this one. But at least for all purposes, it helps us to understand how these transitions occur, and 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 we don't go in a lot of details, information of spectral lines. But I would like to, and this is an example of what that simulation um, is a picture of what that simulation exactly does. But if you are interested in doing a little bit of research, let's say you are curious and you wanna put your hands dirty with some sort of a spectroscopy, Evergreen has a group of students. They are not evergreen students. They are from different places. And then we are doing spectroscopy of certain type of stars and trying to learn their properties. This is done on the side. It's not a graded thing. We might in the future make this more official, but right now it's just for fun. And if
Your
you,
sound is cutting off.
oh, my sound is kind. Can you hear now?
Yeah.
Okay.
Yeah, it kind of comes and goes a little bit.
Oh, really? Oh, thanks for letting me know. I have to. I think is my microphone is getting busted. So I have to buy a headset or so. I would do better next week. By the way, you got my message
Yeah, it
tomorrow.
sounds
I
good
don't.
right now.
Oh, it's getting off again. It's better. Can you hear now?
It was working a little bit. Yeah, it was good.
Okay, sorry.
Yeah, it
Uh,
kind of comes and goes a little bit.
oh boy, yeah. Sorry. I will improve next week. By the way, tomorrow I don't have this chat room because of the exam, and I will probably be driving stuck in traffic somewhat. So the subject, tomorrow's subject, I will explore on Monday. But what I was saying is, if you would like to put your hands in, in some research, in astronomical research, if you have a computer, if you have the time, if you have the curiosity, Evergreen has a group of students doing this type of research, and we are trying to learn how a particular type of star has been behaving in the last 15 years. We have the data and we are working on it. It's quite fun, but we do it in the free time, so we don't have a lot of free time, but we try to do it. Okay. So, having said that, who's gonna do the exam at midnight? It's opening at midnight. The earlier the better. Now you know. Okay, okay, I could do better next time, and then Saturday. All right. All right. So, any other question? Let me stop taping here so we can talk. All right. Good night.